This is Jamb 41. You are welcome to our physical chemistry class. In this video, we are going to look at the topic chemical equilibrium, a very important concept encountered in chemical reaction. We start first by defining the term equilibrium. But first, we should know that equilibrium as a word is a term that suggests equality. That suggests that something happening in one direction is equal to what is happening in its opposite direction. So it's related to chemical reaction. A chemical reaction is said to be in equilibrium if the rate of forward reaction is equal to the rate of backward reaction. In another word, it means that the rate at which reactants react to give us product will be equal to the rate at which the product reacts to give us back the word reactant. So you see, there is a concept of reaction velocity, there is speed of reaction, which is equal because rate of reaction has to do with what? With speed, alright, of velocity of reaction. Because under reaction kinetics, we learned that the rate of reaction is the rate at which the concentration changes with respect to what? Time. And this deals with speed. Is that okay? Alright, now it's important for us to know generally that equilibrium, chemical equilibrium is a reversible process. Okay, reversible process. And that's why in almost all chemical equilibrium reaction we represent it with double arrow, where one line is pointing to the right, that is the product side, and then the other is pointing to the what? To the left. You can see A and B reacting. In the forward direction, we're getting C plus D as the product, and then in the backward direction, C and D, which are the products, are reacting to give us what? A and B, the reactants. So you can see the forward reaction, we've decided to use R subscript F for it, and then the backward reaction, we are using R subscript B. At equilibrium, these two rates are expected to be equal. Now, at equilibrium, there are no observable transformation, no perceptible change, because what is happening there is equal. So you cannot really detect a specific change at the point of what? Chemical equilibrium. The chemical equilibrium is said never to go to completion. If a reaction is in chemical equilibrium, such reaction never goes to completion. Alright, now, at chemical equilibrium, just like we saw from these schemes shown on the board, it's very clear that the rate at which A and B react, giving us C and D, is the same as the rate at which C and D react to give us what? A and B. Hence, we represent the rates in this format at equilibrium. That R subscript F is equal to R subscript B. This condition is at equilibrium. In the next video, we are going to talk about Goldberg and Waec's law of mass action. After stating that law, we shall derive the equilibrium constant in terms of concentration, K subscript C, a very important constant in the study of chemical reaction. We now want to look at the law of mass action stated by Goldberg and Waec in 1864. According to them, the law states that at constant temperature, the rate of reaction is directly proportional to its active masses. Now, the active mass here is in terms of concentration of the reacting substance. Now, we can state this law in terms of the reaction velocity, where it states that the velocity of a chemical reaction is proportional to the product of the active masses of the reactants. You get that right? The rate of reaction is proportional to what? Active masses of the reactant. Now, to understand this law better, we want to look at this reaction scheme on the board, where reactants AB are reacting to give us what? BC. And of course, you know, as chemical equilibrium, there is a reversible reaction where CD, which are the product, are now reacting to give us what? AB. Now you can see the line here, forward and backward. In the forward direction, we have R subscript F representing the forward rate of reaction, accompanied with its equilibrium constant K1 in the forward direction. And then of course in the backward reaction we have RB representing the rate of reaction in the backward direction, and then K2 representing the equilibrium constant in the backward direction. C subscript A, C subscript B, C subscript C, and then C subscript D. We are going to take them as the concentrations of reactants A and B and the concentration of products C and D. Now I want to apply the law of mass action to this equation. Of course, you know, according to Waec and Goldberg, rate of reaction is directly proportional to what? To active masses, which we're going to use concentration C for it. And of course, you know, if that is the case, then our R will be equal to Kc, where K is our constant of proportionality there, which in this case is going to represent our equilibrium constant. Okay, so let us take the forward reaction and apply the law of mass action to it. And in the forward direction, the rate of reaction, which defines our reaction velocity, is directly proportional to the product of the concentration of the reactants, Ca and what? Cb, of course. We need to raise the concentrations to the power of the number of moles for each of them. Then, if this is the case, according to the law of mass action, introducing our equilibrium constant in the forward direction, Rf, that is the rate of forward reaction, will now be equal to the equilibrium constant in the forward reaction times the product of the concentration of the reactants Ca and Cb. We can write that similar for the backward reaction as well too. Then the backward reaction, you can see that giving us this equation 2, okay? Now our rate constant is K2 in the backward direction. So this is the application of law of mass action to this reaction on the board. In the next video, we're going to look at this equation expressed in terms of the equilibrium constant Kc, where we need to apply the fact that at equilibrium, Rf is equal to what? Rb. Then we'll walk around the equation to get our equilibrium constant for the whole reaction. We already established from the law of mass action that the rate of reaction is equal to the equilibrium constant in that direction of reaction, right? Times the product of the concentration of the reactant. We had equations like this for the forward reaction and this for the what? Backward reaction. Now we know that at equilibrium, the rate of forward reaction is equal to the rate of backward reaction. It therefore means that we can equate Rf to what? Rb. Rf value is this term. That is the forward equilibrium constant K1 times product of the concentration of the reactants A and B. And that will be equal to R2, where R2 is K2, that is equilibrium constant in the backward reaction times the concentration of the products. Alright? That is the product of the concentration of the products. Now, having equated these two terms, we can rewrite this equation in such a way that we have K1 divided by K2. Now, if I am dividing K1 by K2, it means I will divide this concentration Cc times Cd by Ca times Cb, so that the equation will look like this. And then we cross multiply this term, you will still get this, so you are mathematically correct. Now, the ratio K1 divided by K2, that is equilibrium constant in the forward reaction divided by equilibrium constant in the backward reaction, will still give you another constant, because we have constant divided by constant will give you a constant. Just like you having 6 divided by 2, it's going to give you 3, which is also a constant. Now, K1 divided by K2, we refer to it as the equilibrium constant in terms of concentration, K subscript C, which is what we are looking for. We are interested in obtaining a very important constant when dealing with equilibrium. Now, having said that, we can now substitute for K1 over K2, replacing it with what? K subscript C. And that will give us this equation that the equilibrium constant in terms of concentration is equal to the product of the concentration of the products divided by the product of the concentration of the reactants. This equation is very important, equation 3 star. Take note of that, okay, for calculation purposes. Now, we want to take note that the rate of forward reaction equilibrium constant is equal to the reciprocal of the backward reaction, that is the reversible reaction equilibrium constant. Now, if we are dealing with gases, you know that we talk in terms of what? Partial pressure. If you're dealing with what? Gases. Hence, this Kc can be written in terms of Kp, where Kp is equilibrium constant in terms of pressure, partial pressure. Then every concentration term will be changed to pressure term. In fact, that equation is obtained from ideal gas equation. We obtain that from that equation because we know that PV is equal to what? nRT. Now if PV, from this term here, if we know that PV is equal to nRT, and then P will now be equal to N divided by what? V, RT. Now P will now give us N divided by V's concentration, so you have CR what? T. You see from here now that we can make concentration subject to the formula, so that concentration will now be pressure divided by what? RT. Does that make sense? So you can actually write these concentration terms in terms of pressure divided by R times temperature, where R is universal gas constant, we know that. And if we walk around that equation, we'll get equation 4 star. So take note of this equation 4 star as well too. It is the equilibrium constant equation in terms of what? Partial pressure. In the next video, we're going to see the relationship between Kc and Kp. In this video, we attempt to derive the relationship between the equilibrium constant in terms of concentration and the equilibrium constant in terms of pressure. That is K subscript C and K subscript P respectively. Now we already have established the value of K subscript C, that is equilibrium constant in terms of concentration. We've also established the equilibrium constant in terms of partial pressure. Now what do we do here? We're going to rewrite these partial pressures in terms of concentration and then see how we obtain the Kc term from it. Now, first of all, we need to recall that from ideal gas equation, pressure is equal to nRT. Now look at it here. If I divide this equation through by volume, I'm going to get that pressure is equal to number of moles divided by volume times RT. And you know, number of moles divided by volume would give you what? It's going to give us molar concentration. Simply concentration of that term. Hence, the pressure of the gas can be written as concentration times R times T, where R is universal gas constant and T the absolute temperature of the system in equilibrium. So we have this equation here. P is equal to CRT. C is number of moles divided by what? Volume. Look at it. So what we're now going to do is to go back to this Kp formula and then substitute for pressure using this equation 1. And that's what we have here, that Kp is equal to, in place of this partial pressure of product C raised to power number of moles of C, we are going to replace concentration of the product C raised to the power of number of moles of that product C times RT raised to that power. So just in place of this P, you substitute CRT. Then this P is raised to power C. It means that this CRT is going to be raised to power C. Look at that term here. Then in terms of this pressure, partial pressure of the product D, you still substitute CRT raised to power D. You can see that, right? Divided by, in place of partial pressure of reactant A, you rewrite it in terms of concentration times universal gas constant times absolute temperature, all raised to power of A, where A is the number of moles of that A, that is a small letter A. Look at that here, and you do same for the partial pressure of B. You get this term. Now, applying power law of indices, you know we can distribute these powers to these terms in brackets, so that this will now become C subscript C, that is concentration of product C, raised to power number of moles of C, which is C. You can say that here. Then this RT term, alright, put them together, raised to power C. Do same for this term, the D term. So it's going to be concentration of product D raised to power of number of moles of D. You can say that. Then the RT term, we put it together, raised to power D. Do same for the denominator. You're going to get concentration of A raised to the power number of moles of A times RT raised to the power number of moles of A. Then times concentration of B raised to the power of number of moles of B times RT raised to the power number of moles of B. Then let us work around this RT term and see what we're going to get. You know, since this whole term are being multiplied, you can apply multiplication law of indices, where you pick one of the RT term and then you add the powers because the bases are the same, RT. So you can see at this point, pick this RT, okay, look at it, and then add their powers, C plus D, multiplication law of indices. Do same for the denominator. We have RT raised to the power A times RT raised to the power B. Pick one of the RTs and then add their powers. Doing that, you will notice something here. Look at this term. This term here, okay, is equal to Kc. You can see that, right? Is equal to what? Kc. Therefore, in place of this term that I've just tried to dot in brackets using the red marker, we can now replace it with what? Kc. That is equilibrium constant in terms of concentration. Then, to this RT term and RT term, you can see that they are being divided. You cannot apply division law of indices. Pick one of the RTs and then subtract the power of the denominator from the power of the numerator. That's going to give us this. And of course, you know that this term, C plus D, is the summation, the addition of the number of moles of the product term in the given equilibrium reaction. And then our A plus B is the summation, the addition of the number of moles of the reactant as given in the what? Equilibrium reaction. Therefore, this term is simply change in number of moles. And the change in number of moles, you can write it in terms of delta N, where N represents number of moles, the delta represents change. Hence, this equation becomes Kp equal to Kc, RT raised to the power, change in number of moles. And that equation 3 star is the relationship between Kp and Kc. You can see the definition of the terms there. Alright, so you can go through that. In the next video, we're going to see under what condition can Kp be greater than Kc, or Kp be less than Kc, or both of them being equal. Of course, that depends on the change in number of moles. In the next video, we're going to look at that. In our previous video, we established the relationship between Kp and Kc, that is equilibrium constant in terms of partial pressure and equilibrium constant in terms of what? Concentration. Because we derived this relationship that Kp is equal to Kc times RT in bracket raised to the power change in number of moles. In this video, we want to compare the numerical value between these two equilibrium constants, Kp and Kc. And before we go into the cases we have on the board, I want to state that in comparing the numerical value between these two constants, it is dependent on the change in number of moles. And you would recall that in a previous video, we stated that the change in number of moles is equal to the total number of moles of product, that is summation of the number of moles of product minus the summation, the total number of moles of the reactant. So take note of this, alright? Now, in case 1, in comparing these two equilibrium constants, we want to look at a case where change in number of moles for the given equilibrium reaction is equal to 0. That is possible if the total number of moles of the product is equal to the total number of moles of the reactant. If that is the case and you find this difference, you will get that change in N is equal to 0. Now, let us go to this relationship now, and then in place of changing N, we substitute 0, you get Kp equal to Kc times RT all raised to the power 0. You take note that this RT term would give us what? 1, because the RT raised to the power 0 is 1. 1 times Kc will give us Kc. And you notice that Kc will be equal to what? Kp. Therefore, when the change in number of moles is equal to 0, a given equilibrium chemical reaction where the number of moles of the product is equal to the number of moles of the reactant, we expect that Kp will be equal to what? Kc for such reaction. Let us consider case 2, where change in number of moles is greater than 0. That is possible if the total number of moles of the product is greater than the total number of moles of the reactant. In that case, change in number of moles will be positive, greater than 0. So if you substitute it into the equation that relates Kp to Kc, we're going to get something like this. And because this change in number of moles is greater than 0, positive, it means that this RT term is expected to be greater than 0. Therefore, to get Kp, did you take note that you are multiplying the value of Kc by another quantity? And what will be the result? It will increase the value of what? Kp. Therefore, for a given equilibrium chemical reaction, Kp is greater than Kc if the change in number of moles is greater than what? 0. In other words, if the total number of moles of product is greater than total number of moles of what? Reactant. Case 3, which is the last here, is when the change in number of moles of the reaction is less than 0. And that is possible if the total number of moles of product is less than total number of moles of what? The reactant in the given chemical equilibrium reaction. What will be the effect of change in N? Change in N, if you find this difference under that condition, will be negative. That is less than what? 0. So if you substitute that negative term for change in N, you take note that Kp will be equal to Kc, open bracket, RT, raised to power change in what? N. Applying negative index law, that's reciprocal law of indices here, we'll get Kp to be equal to Kc all over RT raised to power positive change in what? N. Now watch, if you cross multiply this term, you will be getting Kc value. Did you observe now that to obtain Kc is equal to Kp times a factor which is already greater than 0 in itself, that is RT raised to power change in N. What is the result of this? It simply tells us that to get Kc, you need to multiply Kp by another term, hence increasing the value of what? Kc above Kp. So for a reaction as this, Kp will be less than Kc. In the next video, we're going to look at different equilibrium reactions, right? Where we're going to see the comparison between Kp and Kc in terms of which is greater or whether they are equal. We now want to consider different equilibrium chemical reactions that will help us to see the comparison, right, in numerical values between Kp and Kc as to whether they are equal or whether one is greater than the other. We have 3 cases identified here based on the 3 cases stated previously. Now in case 1, these are reaction equations where we have Kp being equal to what? Kc. Of course, because the change in number of moles for each of these 3 equations on the board here is equal to 0. Now let us find out. In the first reaction is a reaction between hydrogen gas and what? Iodine gas. Now when hydrogen gas reacts with iodine gas, you get what? 2 hydrogen iodide gas. Now how many moles of hydrogen gas we have here? 1. How many moles do we have here of iodine in the reactant? 1. Now you notice that for the reactant, the sum number of moles of the reactant will now be 1 plus 1. Okay, so in the first case, let's say the first case we have sum number of moles of the reactant is going to be 1 plus 1, which is 2. Then look at the product formed. You would notice that the sum number of moles of the product is equal to 2. We have only one compound here, which is 2 moles. So you see clearly that change in number of moles is now equal to 2 minus what? 2, giving us 0. And once change in number of moles is equal to 0, going back to that equation, we established the relationship between Kp and Kc. Have that Kp is equal to Kc, bracket RT, close bracket, raised for a change in number of moles. If change in number of moles is 0, of course, we've already explained that Kp will be equal to Kc for that. You can go through the reaction between nitrogen and oxygen to give us nitrogen 2 oxide, between hydrogen and carbon 4 oxide to give us water, and of course carbon 2 oxide gas here. So go through, you see that in each of these 3 cases here, change in number of moles is equal to 0. Now let us look at case 2 where Kp is greater than Kc. In each of these 2 equilibrium reaction equations shown on the board, you will notice that change in number of moles will be greater than 0. Okay? To be greater than 0. And that is why Kp will be greater than what? Kc. Let's take this first instance and see. This is phosphorus pentachloride. How many moles of the reactant do you have there? For the phosphorus pentachloride, it's 1 mole. So some number of moles of reactant for that is 1. Then come to the product. Some number of moles for the product is equal to, you have phosphorus trichloride plus chlorine gas formed. 1 mole here, 1 mole here. Is that okay? So you're going to have 1 plus 1, which will give us what? 2. You observe now that change in number of moles will be equal to 2 minus 1, which is equal to what? 1. 1 is a positive number, so it's greater than 0. Change in number of moles is now greater than what? 0. Now in that case, Kp is expected to be greater than what? Kc. Now let us look at case 3, where Kp is less than what? Kc. And that is possible if change in number of moles of that reaction is negative, that is less than 0. Now again, let's consider this first reaction, okay, the Haber process reaction between nitrogen gas and what? Hydrogen gas, giving us ammonia. Now take note of this, okay, in case 3, how many moles of nitrogen do we have here and how many moles of hydrogen do we have? 1 is to 3, is that not so? So some number of moles of reactants is 1 plus 3, which is going to give us 4. Some number of moles of products, we have only one product there, is 2. You take note that change in number of moles will give us 2 minus 4, which is equal to what? Minus 2. It's a negative term. And because it is a negative term, if you substitute into the equation relating Kp and Kc, you will observe that Kp will be less than what? Kc. In this video, we are going to solve a question as seen on the board. For the dissociation of water dissociating to give us hydrogen gas and oxygen gas at 1500 degrees centigrade, the value of Kp with partial pressures in atmosphere is 1.87 times 10 raised to the power minus 6. Assuming ideal behavior of gases, calculate a corresponding value of Kc with concentrations in moles per liter. For this problem, we have to calculate Kc. We don't know. So we want to define our parameters, the data we know from the question, okay? Now the Kp value was given to us, so Kp was given to be 1.87 times 10 raised to the power minus 6. And now we were given the operating temperature, so T is equal to 1500 degrees centigrade, which has to be converted to what? Kelvin. To convert to Kelvin, we're going to add 273 to 1500. For that 273, we're going to get 1773 Kelvin. So this is the operating temperature. Now, since we are calculating Kc and we know Kp, then we have to recall that formula relating Kp and Kc which we derived. So we're going to say recall Kp is equal to Kc times RT raised to the power what? Change in number of moles. So we need to select the value of universal gas constant that we're going to use, and we also need to calculate change in N. So let us do that and see. But change in N we know is equal to some number of moles of products minus some number of moles of reactant. So that our change in N will now be equal to number of moles of product. Let's look at it. We have 1 mole of hydrogen here, we have half mole of oxygen. So that is going to be 1 plus half, is that okay? Minus the number of moles of the reactant here. The reactant is just this water molecule and it's 1 mole, so I'm going to put minus 1. If you work out this, 1 plus half minus 1. 1 minus 1 will give us 0, so you'll be left with what? Half. So the change in number of moles for this reaction is half. The value of universal gas constant to use is going to be 0.08205 liters atmosphere per mole Kelvin. Per mole per Kelvin. This is the value of R we're going to use. The reason, the partial pressure is given in the unit of what? Atmosphere. So we need a value of R that is quoted in what? Atmosphere. Now with these terms, we can now substitute into this equation. So it implies that Kp, which is 1.87 times 10 raised to the power minus what? That's minus 6, will be equal to Kc, whose value we don't know, times R, and R is 0.08205 times the temperature, which is 1773. We shall raise this to power what? Half. Making Kc subject to the formula, that will give us 1.87 times 10 raised to the power minus 6. We're going to divide by the coefficient of Kc, which is 0.08205 times 1773 raised to the power half. You know that a term raised to the power half is the same as square root of that term. So with calculator, you can punch the numerator divided by square root of this product. Is that okay? And once you do that, think from here, the Kc value is going to give us 1.55 times 10 raised to the power minus 7. So this is the equilibrium constant in terms of concentration for this equilibrium reaction shown on the board. You are welcome to GMAT 41's physical chemistry class. In this video, we are going to turn our attention to Le Chatelier's principle and how a chemical system in equilibrium can adjust itself in order to counteract any external effect on it when the system is already at equilibrium. On the board here, we have the Le Chatelier-Browne's principle. This principle helps us to study the adjustment of a chemical system to counteract any change that is produced in it as a result of any external factor. We start first by stating the Le Chatelier's principle. Okay, on the board here we have the statement. The Chatelier principle states that for a system in equilibrium, if there is any change in the state of its equilibrium, what will the system do? It will adjust in a way as to give a response so as to counteract that effect. Now, some of the things that can affect the equilibrium state of a system include pressure, temperature, and concentration. At times you may hear something like catalyst. Please, it's very important for us to take note of these, okay? Catalyst does not affect equilibrium position. It does not change the value of equilibrium constant. What catalyst does to a chemical reaction is simply to alter the rate of reaction. It can alter the rate of reaction by helping the reaction approach equilibrium, possibly at an early stage. Is that okay? So what a catalyst does to a chemical reaction is simply affecting the rate of reaction, that is the speed. Is that okay? Either by increasing it to reach equilibrium faster or by decreasing it to reach equilibrium faster. Take note of that. The major factors that affect chemical equilibrium in terms of equilibrium constant include pressure, temperature, and what? Concentration. The way in which these factors affect equilibrium position depend on what the system itself is. What the system itself is modeled according. If the system is in equilibrium, and what makes the system to be in equilibrium is maybe a higher volume, and then there is an external constraint on the system that leads to a lower volume. The system will do something, right, in order to still reach that higher volume initial condition. So at the end of everything, the state of a chemical equilibrium is expected to be maintained. In the next video, we are going to look at how these factors, pressure, temperature, and concentration, affects equilibrium position. In the previous video, we stated Le Chatelier's principle, right? We learned that if a chemical system is in equilibrium and then there is an external factor in the system, which could be pressure, temperature, or concentration, which alters the equilibrium position, the system has the ability to adjust itself in order to what? Neutralize that effect, to counteract that effect, to make the system look as if nothing happened. That helps to bring the system back to what? Equilibrium. In this video, we want to study the effect of pressure on equilibrium position and how the equilibrium will have to adjust in order to counteract that effect of pressure. Before we look at what we have on the board, please, I want to state, and it's important you write. So you can get your pen, get your book, and put this down. For pressure to affect a chemical system in equilibrium, two major conditions are usually expected to be met. One of them is that at least one of the species in the reaction must be a gas. Is that okay? So in a situation whereby everything you have in the reaction, maybe they are solid or liquid, please, pressure would have no effect. Have you taken note of that? Good. Second condition. For pressure to affect the chemical system in equilibrium, the total number of moles of the reactant must be different from the total number of moles of the product. Otherwise, pressure will not have any effect. So if you have a chemical reaction where the number of moles of reactant and product are equal, and you are asked what is the effect of pressure there, no effect. Does that make sense? So let us now consider two chemical systems in equilibrium on the board here and see how pressure effects can make the system to adjust in order to counteract the change in pressure. Now we have this chemical equilibrium here. This is the reaction between nitrogen and hydrogen to give us what? Ammonia. Now what happens, the first thing we need to take note of, here all the reactants and products are gases, right? Now we need to check the number of moles of the reactant and the number of moles of the product, which in our interpretation we are going to convert it to volume. Is that okay? We're going to convert the number of moles to what? Volume. Remember the Avogadro's hypothesis. Equal number of moles contain equal number of volumes and other things. Okay? So we are going to convert this number of moles to volume. Then we'll now check what the effect of pressure will have on this volume. That will now help us to know how the system will adjust to counteract that effect. Now look at the number of moles in the product. How many moles? 4. Because here it's 1 and here it is 3. 1 plus 3 is going to give us what? 4 moles. So the reactant, the total volume there is what? 4. Then look at the product. What is the volume in the product? There are 2 moles there, so this is 2 volumes, alright? And then you see clearly that the number of volume, or the total volume of the reactant is greater than the total volume of what? The product. It is now time. Let us see what pressure can do here if you increase pressure. And then let us see how the chemical system will adjust in order to balance up the equilibrium system. Are we together? Now, this is total volume 4, total volume 2. Generally, if you increase pressure, what will happen to volume? At least the knowledge of Boyle's law will tell us that, right? If you increase pressure of a gas, a chemical system, we expect that the volume will do what? Decrease. I hope I'm communicating, right? So, by increasing the volume of this system already is modeled. The state of this system in equilibrium is such that the number of moles of the product, reactant is higher than the number of moles of what? The product. That is the chemical nature of this equilibrium reaction here. So increasing the pressure of this system, what will now happen? Increase in pressure will lead to what? Decrease in volume. Which means that increasing the pressure of this system, since it is going to lead to decrease in volume, what the system will do now is to move in that direction that you have decrease in volume, so as to compensate whatever is going to happen there. Are you following? Increasing pressure here will decrease the volume. So the system will move in the direction where you have a decrease in volume to assist in order to set it back towards equilibrium. So, having said that now, increasing the pressure of this system, what do we think will happen? The equilibrium will go to the direction where we have lower volume, that is to the right. Which means that if we increase the pressure of this particular system now, the equilibrium will shift towards the what? The product, the right hand side, because you have lower volume there. And then it means that there will be more production of ammonia. Alright, having said that, what if this system were to decrease the pressure? Pressure and volume are inversely proportional according to Boyle's law. So if you decrease the pressure, it means that the volume will increase. The system will now move towards the direction of volume increase. And that is what you saw here, right? The direction of higher volume is the reactant. So decreasing the pressure, the equilibrium will shift to the left to balance it out. So at every point in time, there is a counteraction of whatever the pressure is doing to the system. Let us look at this reaction here. In this case, the number of moles of the reactant is 1. So we have total volume in the reactant 1. And then total volume in the product is 2. Does that make sense? So if you increase the pressure here, what's going to happen? Increase in pressure will decrease the volume of the system. So the equilibrium will shift to the direction where you have a decrease of what? Volume. Remember, that direction in which the volume decreased means there is higher pressure here. which happens to be the reactant. So increasing the pressure of this system, what the equilibrium, the system will do is its equilibrium will now move to the reactant in order to counteract that increase in pressure, because it leads to what? A decrease in volume. So we can say that the equilibrium will shift to the direction that favors a decrease in volume, or to the direction that favors what? An increase in pressure. Then again, in the other way around, if you now decide to decrease the pressure of this system, what is going to happen? Volume will increase also, so the equilibrium will now shift to the direction of increase in volume. Remember, the direction of increase in volume is the same as the direction of decrease in pressure, right? Which simply means that we are saying that the equilibrium is going to shift, in this case, to the right product, favoring the production of more nitrogen 4 oxide. So that's how we interpret the effect of pressure on a chemical system. Please do not forget the condition for which pressure is expected to affect a chemical equilibrium. In the next video, we're going to consider the effect of temperature and concentration. And now, in this video, we want to look at how temperature affects a system in chemical equilibrium, either by increasing the temperature or decreasing the temperature. Now, for us to study that and understand how changes in temperature can affect a chemical system in equilibrium and what that system will do in order to counteract that effect, it is very important for us to understand endothermic reaction and exothermic reaction. We know that an endothermic reaction is one in which heat is absorbed by the system, while an exothermic reaction is one in which heat is given out from the system. That is, heat is evolved. Now, on the board we have two thermochemical equations, one representing endothermic reaction in the sense that the change in enthalpy value, the heat content, is positive. So we look at it as if it's absorbing. Is that okay? And it's absorbing in this case in the forward direction. That is one very important secret. Anyway, I'm going to state that clearly. And then the second one, right? The enthalpy change, that is the heat content of the system, is negative, which suggests exothermic reaction. But the exothermic reaction concept there is in the forward direction. Now, what should you know so that understanding the effect of temperature on a chemical equilibrium will be much more clearer according to the Chartelier'S principle? Now, you listen to this. You might choose to write it down, okay? Because I'm just going to give you a summary of what we have on the board, okay? In general, if a thermochemical equation is given to you, you have to study the effect of temperature on the equilibrium of that reaction. What you want to know first is whether the reaction's heat content, if it is positive or negative. Do you get that? Like in this case, if it is positive, what does that mean? It means that in the forward direction, we have endothermic reaction, which means in the product will be referred to as being what? Endothermic. That is, the forward reaction is endothermic in this case, where the heat content is what? Positive. Therefore, we are left with saying that the backward reaction will be what? Exothermic reaction. Let us look at the second case. If the equilibrium thermochemical equation has a negative enthalpy change, that is heat content, look at it, negative. You know, generally negative suggests exothermic reaction, is that not so? That exothermic reaction is in the forward direction. Does that make sense, right? Then the backward direction will now be what? Endothermic. Which means in this second reaction, being that the heat content of the system, that is the enthalpy change, is negative, then if you move in the forward direction, the product direction, will be what? Exothermic. While the backward direction, which is the reactant direction, will be taken as what? Endothermic. Then listen to this, please. Get your pen, get your book, and put it down in writing. Once again, it is stated here, but I want to re-emphasize on it. According to the Chatelier principle, generally, if you increase temperature, it favors the endothermic direction. Have you written that down? Good. Now, what if you decrease temperature? If you decrease temperature, generally it favors the exothermic direction. So it is not left for you, once a reaction is given to you, check the heat content sign. If it is positive, then you know that in the forward direction it is endothermic, in the backward it is exothermic. Then you now know if the problem is increase in temperature or decrease in temperature, you now know what to say. But if the heat content sign is negative, it means in the forward direction, which is product direction, it is exothermic, and then in the backward direction it is what? Endothermic. So let us consider these two equilibrium chemical reactions on the board. The reaction between nitrogen and oxygen to give us nitrogen 4 oxide. Look at the heat content sign is positive. Is that okay? This is plus 90.4 kilojoule per mole. That's the heat content of this system. What does it show? It shows that in the forward direction it is endothermic. That is the product direction, formation of nitrogen 4 oxide. Alright, if you increase the temperature of this system, where would the equilibrium shift to? Remember, the forward direction is endothermic because of this positive sign. Is that so? So increasing temperature will shift equilibrium to the right, to the product, which is endothermic. And that means more production of nitrogen 4 oxide. That is, more product will be formed. Conversely, that's reversing the process now. If you decrease temperature, what will happen? It will favor the exothermic reaction direction, which means for these, reducing temperature will now favor the reactant, which is backward direction. The equilibrium constant K will shift to the left, leading to more formation of nitrogen gas and oxygen gas. Have I communicated? You know, this concept of the Chartelier'S principles and effect of pressure, temperature, concentration, and equilibrium reaction most times looks somehow complex, but of course it's simple. The trick has been given to you already. Equilibrium constant usually shifts in a particular direction, alright, of the reaction that is being affected by what you are doing. Just like I'm trying to explain it. Look at this second reaction now. The enthalpy change, is it positive or negative? It's negative, is that not so? Which means in the forward direction it is exothermic, in the backward direction it is what? Endothermic. Now let us see what temperature does. If you increase temperature, we stated generally that it will favor the endothermic direction, is that not so? Which means increasing the temperature of this system. Since the forward is exothermic and the backward is endothermic, increasing the temperature, then it means that the equilibrium will shift to the endothermic direction because the endothermic direction will be affected. This is endothermic. The increase in temperature will lead to absorption of heat in the reactant part because that is endothermic. Therefore, what is being affected is the reactant part. The equilibrium will do what? It will shift to that direction to balance up, to neutralize, to counteract the effect in order to bring back this system to equilibrium. Now, what happens if you decrease the temperature of this? Decreasing the temperature, according to the Chartelier'S principle, what is going to happen is that equilibrium will shift to the exothermic reaction. And then you know that the exothermic reaction direction for this is the product side because of this negative sign. Is that what so? So, decreasing the temperature will now favor the exothermic direction. And the exothermic direction for this is the product side. Therefore, the equilibrium will do what? Will shift to the side that is being affected, which is the product. What is the result? Formation of what? More trioxosulfate 6. In the next video, we're going to conclude with the effect of concentration on equilibrium. In this video, we are going to look at the effect of concentration on equilibrium, alright? And when dealing with concentration on equilibrium, there is the effect of concentration on equilibrium. The whole idea is whether there is a component that is being added to the reaction system or whether there is a component that is being removed from the reaction system. In either way, the equilibrium is going to adjust so as to help in decreasing the concentration that is being added or in increasing the concentration that is being removed. That is what concentration effect would make the system to do. So let's assume now that you are increasing, maybe in the reactant, you are increasing the concentration of a particular component in the reactant. The equilibrium will shift to the right, to the product, favoring product formation, so that this reactant you are adding will decrease. Remember that I stated that the way equilibrium shifts or move is such that it will reduce the component you are adding or increase the component that is being removed. So if you're adding a component to the system, let's say to the reactant part, then the product will be favored. The equilibrium will shift to the product side so that this reactant you are adding will be decreasing. Is that okay? But then in a case where you are removing a particular component, let's say from the product you are removing a particular component, the equilibrium will have to shift to compensate for that component you are removing. So if it is from the product side that you are removing a component, the equilibrium again will shift to the right towards the product side. Is that okay? To compensate for that component that you are removing. And if it is in the reactant side that you are removing a component, the equilibrium again will shift towards the left to the reactant to compensate for that component that is being removed. We have this example here, this equilibrium reaction. You can see that the reaction between iron and steam. Alright, so in this reaction we have this iron oxide produced and then hydrogen gas. If in a case where this hydrogen gas in the product is continuously being removed, then the equilibrium will shift to the right so as to compensate for this hydrogen that is being what? Removed. And this will continue until all iron has been used up to give us what? The hydrogen. But then if in the other way around it is this steam that is being removed from the reaction system, then the equilibrium will have to shift to the left, to the reactant part to compensate for the steam that is being what? Removed. And this will happen until this iron oxide is being used up. So this is how equilibrium adjusts in a case where concentration of a particular component in the reaction is being what? Altered.